So, welcome to our folding masterclass, same as before. Key points and then a little bit of exam practice, and yeah, you should be ready to go. So folds, very straightforward. You can see clearly some examples over on the right hand side, over in this area, and I'll be referring to those in a little bit. And the fold structures here are obviously all formed by compressive stress, which we've got at the bottom there. So that's the key thing always to remember. Remember, we're pushing towards each other, so that the principal stress component is like that, and that is causing buckling or crumpling of the crust in various ways. That's what we're talking about when we're talking about folding. Our key points, obviously, know your features. Your limbs. If you hold it like that, that's an anticline, and this is one limb. This is another limb down here, and the syncline would be the same, but the other direction, obviously dipping in that direction. The hinge, the trough, the axial plane, they're all on this diagram over here, so you can look at that at your leisure. The next point is all, as I've mentioned, it's all about compression, and I'm not going to bang on about it. It's there for you to read. They commonly occur in the same area as reverse faults, because a reverse fault, if you remember, is a very, very low angle fault plane. If it's a thrust fault, it doesn't have to be. If it's a higher angle, it doesn't matter. But you remember that side here, when you create a reverse fault, I have to push in this direction. Okay, so I'm pushing in that direction, and it goes upwards. So that's the hanging wall that goes upwards, and that is why they are commonly associated with each other. Reverse thrust faults or just reverse faults, because it's all about the same component of stress, a compressional stress component. Folds are obviously associated with mountain building. So in those two key points, you've got reverse faults to remember and mountain building. Now, just to prove this point, in Nepal, in the area of the Himalayas, you have reverse thrust faults. You have napes, which I'll get onto in a bit, or as some people like to call them nappies. They are commonly found together, in conjunction, in the same sort of tectonic setting. So it's linked to tectonics, obviously. And here we are. The nape, or the nappy, as some of you want to call that, is a reverse thrust fault. And remember, your thrust fault is a very, very low angle, less than 45 degrees fault plane. Okay, so that's what's going to be significant for that. They come in all shapes and sizes. You can see over on the right hand side here, we've got a symmetrical fold, asymmetrical. Big difference between those two. Look at this limb here, much shorter than the limb on the left. So that's the key difference. It's not about angle, it's about limb length. Now, over here we've got our overturned fold. So what we're seeing is that one limb here is no longer the right way up, and that's our recumbent fold there at the end. You can see it. So, and there are our key components, and you can almost imagine the stress increasing and folding that over. You can do like a little dance. That's absolutely fine. Oh, and one thing before I forget, you can have some very small versions of these, so always look at the scale. That's going to be very, very important. The other thing to mention is obviously the interlimb angle. So the angle here and here. So this bit, that's going to be very, very important, because they can ask you to measure it, and it will tell you if it's an open fold or a closed fold. So have a look at your notes about that as well. Any fold questions are often linked to the deformation of rocks. That means rocks that have been changed by obviously pressure. Now that means that you're going to have some deforming in a brittle way, so you get fracturing, and these produce tension joints. So if you've got a series of folds, so let's just draw one over here on the right hand side. If you've got a fold like that, you've got tension joints, if it's a competent bed, around the hinge, okay? And the same way a ruler sort of starts to fracture around the edge. The opposite of that is the other type of rock that's commonly formed is a shale, and deformed, I should say. And a shale, obviously very, very different. It will change thickness, it will squash, if you like, and the strain will be visible in slaty cleavage and alignment of minerals. Now that's another very, very common question. I'm just going to show you on this diagram. If you've got the compressive stress, the minerals will line up like this. Okay, I've magnified that up quite a bit, and it's because it's at 90 degrees to that to the stress direction. So the stress direction is here, and obviously on this side as well. Always check, is it a map, is it a diagram? I've said it before lots and lots and lots. They are absolutely key if you are looking at folds. They're so important because they can really confuse you. And can you start to think about what it looks like in 3 dimensions? That feature in 3D is going to be very, very important. So what is it going to look like in a different point of view? You've all done cross sections as well, so that's going to be absolutely essential for those bits. You can't actually read this because I'm in the way, but I'm just going to pause. So the tip is expect some measurement, really, like I mentioned before. So interlimb angle at the previous section here, so interlimb angle, or it might be the length of a particular limb in here somewhere. It might be the dip of the axial plane, something like that. That one's at 90 degrees, which I've just highlighted on there because it's if that's a horizontal line, that's 90 degrees. So you know that's going to be something to expect as well. Next slide will be all about the exam. Question. Thanks. Welcome back to the fold masterclass in the exam skills section. You can see here clearly at the top, fold questions involve maps, diagrams, photos. So what is your point of view? Are you looking from above on a map or from the side? You can see the diagram in front of us here, and this is clearly got a section which is missing. And you know the map view is looking down on this surface here, and you know the side view is looking at this surface. So you know box diagrams are very common. You'll just have a quick look, see if there's any other information on here that's useful. Well, you know we've got 2 rock types which you know you can clearly identify up here. We've got a shale and we've got a sandstone. So they are going to behave differently under stress. The first question here, it says indicate clearly. So we've got to do something obviously with figure 4a, the position of the fold axis and the axial plane trace of an antiform using the symbol and the key. So we're using this here to put on the antiform axis, and you know have a look at your notes, but you know it needs to bisect or bisect the fold or go down through the hinge. So you know this area here is going to be absolutely key, and you know you'll be able to do this easier than I will because I'm doing this freehand, but you're probably looking at an area down through the core of the fold, if you like. So you can add that in, and you can use the symbols there that they've given you. Be aware of what that antiform symbol looks like, because that triangle is key. If it's a syn form, it's the opposite. The triangle points are meeting in the center. So the next point, or the next question I should say, is an explain question, and it's worth 2 marks. So we're looking at 2 points, and there is clearly a bed of shale, and we need to say about the outcrop width. So we're looking at the top of the sequence. You can clearly see that there is an outcrop width change, and it's looking at this area here and this area here. Now clearly you can see that that is wider than that area there. Now use what they've given you. It's clear there is a difference between those two, and if you're not quite sure, you know, look at the actual angle here. Yeah, so there is clearly a difference in dip angle there to dip angle going down in this direction. So that is going to be key in your response to that one. Point 3, which is here, or part 3 I should say, is draw in the geological boundaries. That's bedding planes. So these ones here, 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 and here are going to be key. Now remember that no matter which orientation we go in, these are parallel. Yeah, so when we draw them on here in this section, on the new section over here, somewhere in this zone, those also need to remain parallel. So we need to draw those on, and it's only worth a mark. It's actually quite straightforward, but have a go at it, and you'll see the mark scheme on the next slide anyway. But you know, if I draw the first one on for you, again, I'm doing this freehand. You would be using a ruler, but we need to keep it parallel with the surface. Okay, so there's the first one on for you. The last question really is the one I want to focus a little bit of time on, which is, and it's asking to describe the nature of the folding. Okay, so obviously we know all folding is about compression, so you might want to start by mentioning that, but it's also giving you a clue as to what it wants you to focus on. It wants you to refer to the strike, dip values, type of folds, axial planes, limb lengths, and fold symmetry. So, and that's 4 marks. That's giving you basically your points that you need to mention. So we can talk about limb lengths, for example. Well, there's clearly a difference, isn't there? So these are clearly asymmetrical folds. I haven't mentioned the type of folds or dip values. You can measure those. Remember, you've got a protractor. You can do that and put those in. I'm going to let you have a go at the rest of that one, because I think that's quite a straightforward question, and we'll have a look at the next set in a minute. Okay, final fold related question, just very quickly. I'll give you a tiny little bit of help with this one. You can clearly see this is related to figure 4a that we've just been looking at. The sandstone and shale bed are key. So we've got this shale and sandstone on the image here, and you can clearly see there's this sort of undulating surface. So that undulating surface is going to be absolutely key, and the sandstone's below there and the shale's above. Now that is clearly a sedimentary structure, so look at the sedimentary structure masterclass and have a look at you know, this looks like it might be post-depositional, so there's your little clue. Now the next question, which is explaining how that sedimentary structure might be related to figure 4a and establishing the relative ages. So really we should be using this maybe to work out which way up it is it the correct way up, and you know, which one of those is which order, what's the order of events, because that's what relative age is. So I'll leave that one there for you. Enjoy, have a go, and have a look at the mark scheme on the next slide.